I'm going to go ahead and define something called the lower triangular entries of a matrix. Okay. And for now, we'll just focus on square matrices. You can define lower triangular matrices for non-square matrices, but are all the entries, could you guess what we say the lower triangular? If you were to draw a square matrix, which are in the lower triangular? Yeah, we're going to call that strictly lower triangular because it's a strict inequality. With that said, could you guess what we say? It's not a strict inequality. Greater than or equal to k. So, aka all entries on or below what? The main diagonal. Okay, let's go ahead and extrapolate. A strictly lower triangular entry, and yes, there should be a hyphen between the two of this because this lower triangular is an adjective, is a compound phrase adjective of this word. You can read any style guide to figure that out. Strictly lower triangular entry of A are what? Are all entries what? AIK such that I is strictly greater than k. What's another way to say that in terms of the main diagonal? Yeah, and why don't we use the word strictly again? Strictly below the main diagonal. Does anybody see a definition that is just waiting to be made? Here, and let me set you up for this with a creative use of voice inflection. If the strictly lower triangular entries are the ones below the main diagonal, then all right, so can I leave that for you as homework? What's the homework, Arash? Arash, you sound so much like Misha right now. That's weird, man. What's the homework? Come up with a definition for what? And also upper triangular matrix. Excuse me, upper triangular entries. Okay, so extrapolate to define upper. Yeah, maybe I'll be really, really lazy. Watch this, you ready? Strictly upper triangular entries. So both the upper and the strictly upper. And then am I over here or am I over here? All right, so far we have what we call a diagonal matrix. We have what we call lower triangular entries. We have what we call upper triangular matrix. Can you guess what other type of matrices we might define? So we had the main diagonal entries allowed us to define what we call a diagonal matrix. The lower triangular entries allow us to define a lower triangular matrix. So this is going to be a definition that we have, definition 3.8, lower triangular matrix. And in this case, why don't we call that matrix L to hearken to the idea that it's lower triangular. In general, all of these will be n by n, and we'll talk more about that in lesson 11. So let's let L be an element of R n by n is a given square matrix. So we say L is lower triangular if and only if, can you guess when we say L is lower triangular? Okay, let's use the entry operator. And then I'm going to go ahead and say that the ith entry, I like to use the script L. Can you guess why I don't use this one? It looks like a 1, it looks like an L, it looks like an I. Not sure what the hell it looks like, right? So I like to use the script when I'm doing notation for the letter L in lowercase. Could you guess what we say a lower triangular matrix is? What is a diagonal matrix?
Just the diagonal.
Just the diagonal is allowed to be non-zero. Is it guaranteed to be non-zero?
No.
No. In fact, the zero matrix is a diagonal matrix, right?
Yeah.
The square zero matrix is a diagonal matrix. What's the condition, though, in the diagonal matrix? Only the main diagonal can be non-zero. Could you guess then what a lower triangular matrix the condition is?
Only those entries can be non-zero.
Only the lower triangular entries could be non-zero. What's a way to impose that entry by entry? What must be true? If you're strictly above the main diagonal, what does that mean about your row and column index?
Your
column is bigger than row, then all of those entries must be 0. What would that look like if we wrote it out? In a lower triangular matrix, which ones are allowed to be non-zero? Yep, diagonal, the main diagonal, and below it, everything else must be 0. What's the last one? Every single one of these definitions requires what type of matrix? Square. You got it. And then I can hear Trefethen. There's a guy named Trefethen in this field. I can hear him yelling at me right now because he likes to use M for his row for square matrices. But all right, Trefethen. What's that? No, he's still alive. One of my graduate student colleagues published with this man. Yeah, I guess I'll just leave it like that. Yuji Nakatsukasa. All right. The next one we're going to talk about is we'll do one more together, and then we're going to go on to Yeah, we're not going to do multiplication yet. That's a very, very complex idea. But you know what I would like to do? I'd like to actually define what we call a unit lower triangular matrix. I could do multiplication, Misha, but I actually want you to understand what you're doing. My claim is that every mathematician that has ever taught me multiplication out loud matrix multiplication out loud has butchered the concept. They taught that matrix multiplication is an inner product between the rows and the columns. That's just a butchering. It's the worst way to think about it, and we'll get into that later. So one of the things I want to say is what we call a unit lower triangular matrix. Triangular matrix. L, because it's lower triangular. Could you guess what size these things have to be? What is every special matrix that we've defined so far? What size is it? Square matrix, n by n, is a lower triangular matrix. What does it mean immediately when I have a lower triangular matrix? Yep. Watch this, though. When we use the word unit, we say that Lik is equal to 1 if I equals k. AKA, it's a lower triangular matrix with what property? Whose main diagonal elements are what? Equal to 1. This is related to LU factorization. These are really, very famous. In fact, most people would see this is called Gaussian elimination. So if you've taken another, anybody ever been in another linear algebra class?
No.
Oh God. Eliminate, something like that, right? Nobody? The first day in another linear algebra class you would do Gaussian elimination. My claim is that you're multiplying by a very, very strategic set of unit lower triangular matrices. And we'll see this today, right? Could you guess what's missing here? What are the two definitions that we haven't done yet? Yeah, so please define for yourself what an upper triangular matrix is, and what else?
Everything the opposite of lower triangle.
Yeah, I actually don't care so much about unit upper triangular. That's kind of a special case. Could you guess what I would say about a strictly upper triangular matrix?
That is less than 4.
What must be true about a strictly upper triangular matrix? What would be true about the main diagonal? Main diagonal would be 0, right? Because only the ones in the strictly upper triangular portion would be allowed to be non-zero. That comes up in what we call Jordan form. It's a very famous matrix called nilpotent, which we'll talk about.